Today I will talk about the possible use of carbon nanoanions as donor-acceptor diodes in dye-sensitized solar cells. My name is Miquel Solà and I'm working in the Institute of Computational Chemistry and Catalysis of the University of Girona. This is the outline of the talk. After an introduction, I will discuss the photoelectron transfer processes in the smallest carbon nanoanion, C60 at C240, and its lithium plus doped counterpart. Then I will present the results we obtained on the reactivity of this species, and I will finish with some conclusions. So let's move to the introduction. Before the discovery by Kroto, Kahl, and Smalley of the C60 fluorine in 1985, only two allotropic forms of carbon were known, graphite and diamond. Now a number of carbon nanostructures, which include various low-dimensional allotropes of carbon like fluorines, carbon nanotubes, and graphene, are known. Of the same family of fluorines are carbon nanoanions that were first synthesized in 1992. They are formed by several concentric shells of fluorines in a structure that resembles a Russian doll. One of the applications of these carbon nanostructures is in the area of organic photovoltaic devices. Fullerenes, for instance, are used in dye-sensitized solar cells as acceptor molecules in two possible strategies: the so-called bulk heterojunction, where the donor and acceptor moieties are not covalently bonded, and molecular heterojunctions. In molecular heterojunctions, donor and acceptor are covalently linked in what is known as a donor-acceptor diode. The use of molecular heterojunctions allows a better control of their structure and charge mobility. When the light hits a fluorine diode, in many cases there is a local excitation from the HOMO-1 to 1 high in energy local excited state, which then relaxes to the lowest local excited state. This is what indicates the blue blinker arrow in the scheme. Next, from this local excited state, a transfer of one electron from the HOMO of the diode to the HOMO-1 takes place, generating a charge transfer state in which the donor moiety is positively charged and the fluorine is negatively charged. This is the red blinker arrow in the scheme. Finally, there is a transfer of one electron from the LUMO to the HOMO, and the charge transfer relaxes to the ground state in what is called the charge recombination process, and this is indicated by the green blinker arrow in the scheme. A good diode for a molecular heterojunction solar cell should absorb solar light efficiently and have a long-life charge transfer state. Carbon nanoanions were discovered by Jima in 1980 and synthesized by Ugarte in 1992. Synthesis of double and triple shell carbon nanoanions were reported in 2000 by Mordkovic. Carbon nanoanions have higher fluorescence quantum yields than C60 from visible to near infrared regions, which makes them promising for photovoltaic devices. Functionalization of carbon nanoanions is needed to improve their solubility and to generate donor-acceptor diodes if they have to be used in photovoltaics. Are carbon nanoanions easy to functionalize? In general, the larger the fluorine, the smaller the reactivity because carbon atoms are less pyramidalized. Still, a 1,3D polar cycloaddition to carbon nanoanions was reported in 2013, and later on 2+1 cycloaddition of nitrogen, cyclopropanation, radical additions, oxidation, etc. were also observed in carbon nanoanions. In case carbon nanoanions were not reactive enough, there is always the possibility to encapsulate lithium plus inside the carbon nanoanions, since it has been shown that the lithium cation encapsulated in C60 is more reactive than C60 itself. The question we would like to answer here is, could carbon nanoanions be used as acceptors in donor-acceptor diodes to design efficient molecular heterojunction dye-sensitized solar cells? To perform this study, we have to characterize excited states. To this end, we started with the semi-empirical Endohedral method, and then we move to time-dependent density functional theory. By comparing with experimental data, we have recently proved in this physical chemistry, chemical physics paper that the general picture of the photoinduced charge transfer in fullerene diets processes are well described by time-dependent density functional theory using hybrid and long-range corrected functionals like CAMB3LEAP that contains a 90% of Hartree-Fock change at short range and 65% of Hartree-Fock change at long range. So how do we characterize the nature of excited states? The one electron transition density matrix is the key quantity. The element P alpha beta OI of this matrix yields the probability of finding an extra electron on the beta atomic orbital and a hole on an alpha atomic orbital in the transition from the ground to the excited state. From this quantity and the overlap matrix, we can compute the extent of localization in fragment F in the transition from the ground to the excited state, XF, and also the charge transfer and charge separation. Now let's move to the results of the photoelectron transfer processes in C60 at C240 carbon nanoanion and its lithium plus doped counterpart. So the first calculations we did were done with the Endohedral semi-empirical method. As you can see in the table, for the lowest local excitation and the brightest local excitation, the experimental results match the theoretical calculations quite well, with errors lower than 0.2 electron volts. The oscillator strength from the brightest local excitation is 0.37, and this is an important result. This graphic represents the first 300 excitations in C60 at C200 carbon nanoanion. Most correspond to the local excitation in the C240 cage in olive color, some to the local excitation to C60 magenta color, and the rest are charge transfer excitations. In the 2.5, 2.6 electron volts region, we have local excitation in C240 with a sum of oscillator strength as high as 6.1. Therefore, C6 at C240 carbon nanoanion absorbs sun energy more efficiently than C60 does. Among charge transfer excitations, there are two types: those that generate a positive C60 and negative C240 in blue, and those that generate a negative C60 and a positive C240 in red. The blue ones, so those that have C60 plus, C200 minus, are 0.5 electron volts lower in energy as compared to the red ones, leading to C60 minus, C240 plus states. The higher electron affinity of C240 as compared to C60 explains the lower energy of the C60 plus, C240 minus charge transfer states. Remarkably, the blue ones lie in the same region, 2.4, 2.6 electron volts, as local excitation states responsible for strong absorption. There are local excitations in C240, and they can be effectively populated despite having weak oscillator strength. Two important aspects of charge transfer states in C60 at C240 carbon nanoanion have to be mentioned. First, reorganization energy is small, 0.70 electron volts, which favors charge transfer processes. The low reorganization energy is ascribed to the extent pi conjugation and rigid molecular structure of carbon nanoanion. Second, charge transfer states are not particularly stabilized by the solvent in carbon nanoanions. Solvent effects in general stabilize charge transfer states much more than local excited states. However, charge transfer states in the carbon nanoanion with a positive Fullerene cage and a negative one, both having the charge well delocalized, are not much stabilized by solvent effects. For the limiting case of water, charge transfer states are stabilized by only 0.14 electron volts. And now, what happens when we include a lithium plus cation inside the C60 at C240 carbon nanoanion? The main result is that the lithium plus at C60 minus at C240 plus charge transfer states with a charge transfer of 0.8.9 electrons are significantly stabilized by about 0.8 electron volts, and they become the lowest singlet excited states at 1.72.7 electron volts. Moreover, 3 of these states at 2.2 electron volts can be directly populated because they have an oscillator strength of 0.17. Of course, the lithium plus, C60 plus, C200 minus charge transfer states lie now very high in energy because of the repulsion between the lithium cation and the positively charged C60. On the other hand, the local excited states at C60 or C240 are almost insensitive to the encapsulated lithium plus. Finally, a new type of charge transfer state corresponding to the HOMO to the LUMO to LUMO plus 3 transition that generates the lithium at C60 at C240 positively charged, the last one, this state appears at 2.79 electron volts in green color. This conclusion applies to higher carbon nanoanions. The higher the carbon nanoanions, the lower the charge transfer transitions. Those that encapsulate C60, 3 on the left, generate lithium plus at C60 minus at the fluorine, the last fluorine, the outer fluorine positively charged, while those that encapsulate C240 or C540, 3 on the right, yield charge transfer states with neutral lithium and inner fluorine and positively charged outer fluorine. In summary of this first part of the talk, lithium encapsulated carbon nanoanions absorbs sun energy more efficiently than C60 and directly generate charge transfer states. Therefore, carbon nanoanions are potentially better acceptor moieties to be used in donor acceptor diodes in molecular heterojunctions dye-sensitized solar cells. The question now is, it is possible to attach a donor in carbon nanoanion to generate a donor acceptor diodes? So let's move to the results of the reactivity and a standard Diels-Alder reaction in the C60 at C240 carbon nanoanion and its lithium plus doped counterpart. Here we want to know whether it is possible to functionalize the smallest carbon nanoanion and their lithium plus doped counterpart with a Diels-Alder reaction. The carbon nanoanion acts as a dienophile in this Diels-Alder reaction, whereas the diene is cyclopentadiene. We want also to answer the question whether the inner C60 acts as a Faraday cage. If C60 acts as a Faraday cage, the lithium plus will have the same effect on the reactivity of C240 fluorine as that on the carbon nanoanion C60 at C240 carbon nanoanion. The method used involves geometry optimizations at the PBE functional with dispersion corrections included and single point energy calculation with the M06 functional. So first we have to look how many different bonds do we have in C240. To answer this question, the best way is to plot the molecule and to generate the Schlegel diagram of the carbon nanoanion C60 at C240. From the Schlegel diagram, we see that there are 5 different bonds. 4 correspond to 6-6 bonds, and 1 is a 5-6 bond. We have calculated the enthalpy barriers for all bonds, and clearly the 6,6 bond B is the most reactive. In addition, is the only one that is thermodynamically favorable. So we have looked only the reaction to this bond, and the results show that first, C240 is less reactive than C60, and this is because it has smaller pyramidization angles. Second, lithium plus lowers the barriers and stabilizes the product in all cases. The reason is the reduction in the LUMO energy of the cage by the lithium plus encapsulated. Third, as we can see, the reactivity of C240 does almost not change by having C60 encapsulated inside. Fourth, however, when we encapsulate lithium plus, the reactivity of C240 changes significantly with respect to that of C240 in the carbon nanoanion. Therefore, we conclude that the effect of lithium plus is partially shielded by C60, which is not a perfect Faraday cage. So let's go to the conclusion, and in summary, we have shown that the general picture of the photoinduced charge transfer in fullerene diodes are well described using time-dependent DFT methods with hybrid and long-range corrected functionals. C60 at C240 absorbs sun energy more efficiently than C60, and two types of charge transfer states are then generated: C60 plus at C240 minus and C60 minus at C240 plus. C60 plus at C240 charge transfer states lie in the same region, 2.4, 2.6 electron volts, as local excited states, and they can be effectively populated. Lithium plus C60 minus C240 charge transfer states can be directly populated. Lithium plus lowers the energy barrier for the transition state and the energy of the Diels-Alder cycloadditions. And C60 shields partially the lithium plus charge, thus fullerenes are not perfect Faraday cages. As a whole, we can say that lithium plus doped carbon nanoanions seems to be excellent candidates for donor acceptor diodes in dye-sensitized solar cells. So now let me move to the acknowledgements, and I want to acknowledge all who contributed to this work, and especially Dr. Olga Stasiuk, Dr. Anton Stasiuk, Professor Alexander Wojciuk, who are responsible for the excited state calculations, and Dr. Jesus Antonio Luque Urrutia and Dr. Albert Poetet that performed the calculations on the reactivity of C60 at C240 carbon nanoanions. Finally, I am grateful to the institutions that provided the funds to perform these calculations and all of you for your attention. Thank you very much.